So welcome to the Bresenham Triangle computer graphics practice video, and in this task we'll be trying to rasterize triangles. Now if we have a triangle, so any triangle, we have three vertices, vertex 0, let's put vertex 1 here and vertex 2 here, and there are three lines this way. And if our triangle is somehow rotated, so for example maybe it's something like this, then we still have a way where we can kind of order the vertices in a way that our vertex 0 will be the leftmost, then we'll have vertex 1 because this is the middle one, and vertex 2, the last one there. And whatever way this triangle is rotated, we can order those vertices from left to right. And this will create us kind of two triangles where this middle vertex kind of splits the original triangle in two. There is some point here as well. So now we have three lines, and our first line will be this one, second line this one, and both of those will share this line. And this is important because the algorithm we're going to implement will work like this. We're going to move on two lines at the same time. And first we're going to move on that line and this line from left to right. And we're going to find points on those lines that kind of share the x-coordinate. So for example, if we have this, let's take this one, this grid of pixels here again, and I don't know if maybe this will help, maybe not. So we're going to find out that first we need to color what this pixel is on the lines of the triangle, then those two, so those will be quite near each other, and then we're going to find this pixel, and now we have a horizontal line going from this pixel to that pixel. So this line we also rasterize. And this is the main idea of this algorithm. Then we're going to continue. We're going to see that this pixel is on this first line, this pixel, and maybe that's like this pixel. So, and on the second line is this pixel, this pixel, this pixel. And between all of those pairs of pixels, there are vertical lines which we fill in. When we get to the midpoint of this vertex here, then the line on the bottom continues as it was. This we're not going to change. From V0 to V2 is going to be the same line all across the algorithm. But the first line here, this line has ended, and now we're going to exchange that line with the line from V1 to V2. So this will be our second line, and we'll do the same thing. We'll color the pixels and the corresponding pixels on the bottom line and fill in vertical lines between them. And this will fill the triangle. Now let's see how this looks like in code. So if you download the JavaScript base code, you're going to see a couple of things here. So I have added also this classes.js. So there are some classes which you might find helpful here because we'll be using Canvas, not 3JS. I implemented a few neat classes. So a color class, you can add colors, multiply colors, return a multiplied color, or copy a color. And we also have a vertex class, so that maybe I should have called it a point I don't know, this is basically, these will be the points on the, we'll use this class to keep track of the points on the lines. And it has, I don't know, swap width, copy, distance, rotate, slope, steep. So, yeah, so if you have another point, you can see if there's a steep line or a non-steep line from the current point to that point. Okay, but you can see if you want to use those functions or write your own functions. It's up to you, and you don't need to use all of those here. Okay, so what we have, again, we have this context, Bresenham context. We'll have those 3 vertices, so it will be some arbitrary triangle. There are also colors, so if you look at the task description, it's not only about rasterizing a triangle, but it's also coloring it with different colors, so not just a single red triangle. And we'll get to this in a moment as well. Then in this draw function, we are just rotating some triangles. So this is also this draw triangle. This is the canvas drawing calls, and it will rotate the triangles to show that it doesn't really matter this ordering. And also there are different cases again for steep lines, non-steep lines, ascending, descending, and if you rotate it, then all of the lines become one or another at some point. Okay, you can also see that there is this delta here. So this is quite like some of you might have done this, that you want to update at a certain time. So you see that if a certain time has passed, then you actually rotate. Otherwise, like you don't. So using this is delta greater than 40 milliseconds approach isn't the best approach, but I just wrote it here so that you can see that it can do something. But we'll see better approaches in the later tasks as well. So let's see how this works currently. If I put it here, you can see that this is your regular canvas triangle. It won't be colored, it's just like this. And this is what your current algorithm produces, not very triangle-y. But let's see if we can get some idea on how to implement this. So we have this sort vertices function, so this just swaps the vertices in a way that they're ordered from left to right. And then we have this draw Bresenham triangle. So we'll have point 1 and point 2, so those will be the 2 points moving along the edges of the triangle on different lines. And currently we say that both of them start from V0, and we find some distances. We find up a steep, we find the slopes from V0 to V1, V0 to V2. And then we're going to start iterating over x. So what we want to do is we want to find for each x coordinate inside this triangle the points on those 2 lines, and then draw a vertical line from one point to another. For that, we have this Bresenham triangle step function, which should return us the errors that we need for the next step, and the y coordinates that are the coordinates on both of those lines. So I don't want to do much of the task here for you, but well, for example here, like the comments should be quite understandable. Assign the current x and the 2 y coordinates that you just found to the point 1 and point 2 positions. So we can see we have those vertices have a position variable. So we can say that point 1 position 0 is our x that we iterate over, and our point 1 position 1 is our y1, and we do the same thing but with y2 for point 2. Yeah, and so those two will represent the points on the lines. Now we'll get to colors in a moment, but then basically you draw a vertical line and this will color one line of that triangle. What happens here, this is where you reach the vertex 1. So you need to exchange, like the new point 1 will be vertex 1, and we will find this distance is steep and delta error, and now from V1 to V2, so the second line from V1 to V2. And then comes the next half of the triangle, and it's the same thing. Now we draw the vertical lines on the second half of the triangle. And well, this function draws a vertical line given 2 points. And this is the step, so this should do just one step on a line, not rasterize the whole line, but only move to a next x position. So depending on if the line is steep or ascending or descending or non-steep, it will do somewhat different things, because if it's a steep line, then you might need to iterate over many y until the x actually changes, and you can like fill this out yourself as well. You also need to return the error, because you will use this step on the next step as well, so you need to send in the error that you got from the previous step in order for this to work. And yeah, what you can also additionally do is put your Bresenham line algorithm here, and you can draw the outline of the triangle. And don't worry if your vertical lines don't coincide with the outline. I mean, they should, like, relatively, but if there are some pixels that are colored, then that's okay. But what is important is if you're doing the coloring here. So the thing with triangles is that every point on the triangle can actually be represented as a convex combination of the vertices. So I'm going to draw another triangle. So if we have some vertices 0, 1 and 2, then every point inside here can be represented as some convex combination of those. What this means is that all of those three have some coordinates, right? And if you have a coordinate system, then the coordinates, what they mean are they're just like location vectors to those three locations. And this means that you can represent a point here as a convex combination of those three location vectors. And what is a convex combination? So this is just let's say alpha times v0 plus beta times v1 plus gamma times v2, where your alpha, beta and gamma are all greater than 0, and alpha plus beta plus gamma must equal to 1. Actually, some of those can be 0 as well. So, for example, if you want to find this point, then this will be just 0 times v0, 0 times v1, and 1 times v2. If you want to find a midpoint here, then this will be 1/3 of v0, 1/3 of v1, and 1/3 of v2. And those alpha, beta, and gamma will then be called barycentric coordinates, and this is kind of a barycentric coordinate system. So if you want, you can of course find out more information from Wikipedia about this. So, for example, convex combination, it's a linear combination of points, vector scalars, whatever, in affine space, points in an affine space where the coefficients are non-negative and sum up to 1. So, can be any number of elements, just non-negative coefficients and must sum up to 1. So this is a really powerful construction. And also, if you go see like the article on barycentric coordinate systems, you can find some barycentric coordinates in triangles that you can see that the point between those two vertices is 1/2 of one, 1/2 of another, and 0 of the third. And this kind of represents the closeness to some point. So this is why it's it's often easy to confuse. Like if you have a point, do we have such a point here? Not really. If you have a point somewhere here, then it's easy to think that, okay, so it's 3/3 of that one and 3/4 of that one and 1/4 of that one, but it's actually the other way around. So it's kind of the closeness to the vertex. So keep that in mind. But what this allows us to do is kind of find an interpolation or a convex combination over, like this said, whatever values in some affine space. For example, we can have a space of colors, so RGB values. This is also a space, and we can assign the barycentric coordinates to the elements in the color space. Currently here, what we have done is assign them to the position vectors. But the position vectors, they don't have to be position vectors, they can be color vectors as well, or any other value you want to interpolate over a triangle. So what you should do here is kind of find the weights for the colors. So those will be the barycentric coordinates, and then use a convex combination of the colors to interpolate them together and find the color, for those two pixels, and then they will linearly vary along this gradient line. And this should produce you an image that's not here, well, there is a gradient here, but this kind of a triangle where you have a red corner, blue corner, and a green corner, and they smoothly vary, and in the middle there is this middle gray value. So how to actually do that? Well, there are different ways. So one way that's kind of easy to understand but not really computationally optimal is to use the distance. So what we can have is, for example, if we have a triangle, yeah, so E0, E1, and V2, and we want to find out like the barycentric coordinates for some point. Then, well, depending on which way you move across this triangle, if you have vertical lines or horizontal lines. If you have a vertical line here, then the question is, what are the barycentric coordinates for those 2 points? And one like intuitive way to do this is to like find the distance or the length of this line. So I don't know, let's say it's 10, and distance, let's say from of this line. So maybe this is 4. So this will give us that it's the coordinate for this is 4 tenths of V0, 6 tenths of V1, and 0 of V2. The same thing we'll do with this point. We'll find some values for them. So depending again on the length of this line, some peak value for V0, so maybe it's like 0.8 possibly. Then some for V1 it's 0, and for V2 well, it leaves us with 0.2. And then we can interpolate between those two. So where is this? So maybe it would be better to easier to calculate if we put this in the middle of that. So the barycentric coordinates of that will be 0.4 plus 0.8 divided by 2, then 0.6 divided by 2, and then 0.2 divided by 2. That will be 0.6, 0.3, and 0.1, and sum up to 1, and those are the barycentric coordinates for that point. What I did here is just added those two together element-wise and divided by 2 if we say that this is 50% from both of the points on those lines. But you can of course be more clever here. So instead of just instead of finding the distance here, which involves like squares and square roots and whatnot, you can actually find, because we're dealing with the percentage, you can find the projection. So if you are here, your coordinate axes are here, x and y. You can, for example, and this is the these are the actually the coordinates. So it doesn't matter. You can find the percentage on the x-axis. So this will be your entire change in x. This will be your change in x until that point, and you find out how much this amount of change in x constitutes of the entire change of x along the entire line. Or on y, doesn't matter, whichever is easier. Maybe you already have some of the values, like the change of y of this this line. So, for example, like this could be 2, this could be 8, and here we have 6. So this means the entire span of the entire change in y will be 6, and currently we have moved 4 units, so it's 4/6, and that will be 2/3 of that point. So it will be 1/3 of the first point, 2/3 of the second point, 0 of the last point, if we are talking about this line, for example. So you don't like have to find the distance, you can find the percentage on the projection on one axis, and it will give you the same value. It's just computationally cheaper that way. And when you have found well, let's call them weights, then you can kind of take the colors. So point 1 color, you need to assign a color to point 1, color to point 2, and those will be the colors from the vertex 0, 1 or 2, depending on where you are in the algorithm, mixed together via those weights. So if you mix them together, put them for point 1 and point 2, and then draw a gradient line, then it will be correct. So this is the task. In the end, you should get those triangles, and like with all triangles, they should kind of rotate, and this should be the final result you get. So you can see that sometimes if you make an error, there will be this kind of flip of colors when the vertices change the order, so make sure this doesn't happen. But otherwise, yeah, have fun making those psychedelic triangles.